Hi, my name is Richard John. This is an application of random forest regression on inflation prediction. Now, ever since the COVID pandemic, inflation has risen to quite great numbers, which has affected Americans all across the nation. Well, fortunately, since the COVID pandemic, there has been some recovery, with 2023 Americans having the same purchasing power as those in 2019. This is a fact I got from the U.S. Department of Treasury, and this is the source in which I got that statement. However, even still, Americans still feel stretched due to inflation nowadays. Like if you go to a local grocery store, you might see your bananas being double or triple the price, which hence the need to predict the next few months of inflation. As business decisions, consumer spending habits, and even policies by policymakers can all be greatly improved by providing them the information ahead of time on what to expect exactly from inflation. Now, the reason why we might want to apply deep learning to inflation prediction is, as per Alexandria Fernandez Theodorus, Diogo, and some guy I might not say his name correctly, macroeconomic prediction is plagued by nonlinear and non-stationary data, hence the usefulness of deep learning models, which may prove advantageous to traditional stationary linear methods. This is the link to their paper. Now, the following project examines core CPI, which is based on monthly pay, manufacturing amount, total capacity utilization, unemployment, and many more factors. Now, all the data used in this project specifically comes from either the website of the Bureau of Labor Statistics and the Federal Bank of St. Louis. The data range utilized in this will be from January 1st, 2001, all the way to September of 2024. The idea of this project is to observe the use case of random forest regression on the function of predicting inflation. Now, before we can begin, we first have to install OpenPy Excel, as this uses Excel files in order to take all the data inside. And we will also be using models from scikit-learn. So first thing first, we got to load the data. We will use read Excel, pandas function. But even so, when the data was downloaded, not all of them started on the date of the first months of 2001 or January 2001. Some of them have starting points quite before that, all the way down to most likely 1968. But what we want is that all of them start on January 1st, 2001. Hence, we need to take out all of the points before January 1st, 2001. So what we will do is we will create a function. This will take in a data set and the amount of rows to drop and which column to drop them from. And that should fix our data sets. We apply that to all of our data sets right here. We're also going to create a list of months. We're going to use that later to take the timing. And some of the data sets, they will have some months after September of 2024. So we're going to have to pop those out too. Now that we have all the data starting at January 1st of 2001 in the form of lists, we can then create a pandas data frame from them. So we will put them all in function and then actually make the data frame. We can print that data frame out right here. Next, we're going to examine the months over months core CPI. Ideally, we would like our model to show similar trends of core CPI when we actually predict it. So let's take a look at that. Notice here though, considering our model, this project specifically, the month 0 correlates with January 1st, 2001, and month 1 will in turn correlate with February of 2001. Now we're going to scale our data. The reason for scaling is that it helps improve the machine learning, makes it a bit easier for it to learn. Here is our data frame. Here's the shape, 285, 14. Now we can let's make the baseline, which is through linear regression. So we're going to split the data set into a train and a validation set. then we're actually going to put it inside the linear regression, and then we're going to train that on that, and these are our results. Now we're going to compare the scaled validation data set with our predicted set, and we will get a MSE score of 0.00456. This will be our baseline to compare our random forest regression. We create that later on in the tutorial. So we'll just finish our prediction data set, which this will be just a concatenation of our train set plus this prediction. And then we will compare that prediction with the actual course CPI. So if you notice, they're going to be the same because we're using the same train for those first few months. But then later on, as you can see here, they start to diverge because that's where we're actually comparing the predictions with the actual. And as you can see, the predicted does a little bit of jumpy, and then it's a little bit lower. Now, let's take a look at an implementation of a random forest regression model. So before we do anything, we first have to import the random forest regression model from scikit-learn, which we'll be using. Then, just like the linear regression model, we'll be splitting the dataset up into training and testing, with our training dataset consisting of 240 samples, and our test set will consist of 45 samples. Now, in order to learn how to implement random forest regression, I use this link from Geeks for Geeks, and here is our model right here. This model consists of 200 n estimators, which means it uses 200 decision trees. The more n estimators, the higher the value we put in n estimators, the more decision trees we have, and in turn, the more the model is able to learn the complexities that are inside of our data set. Since we set OOB score to true, we're going to take a look at the OOB score or out of bag score. So let's train it. All right, we've trained it. Now let's take a look at the out of bag score and the mean squared error. So our out of bag score is 0.9987. That basically means how well it is at generalizing data that the model hasn't been trained on. So if I were to go pick out a data point that has all the features that we've used here in our project, but the value is not what the model has trained on before, such as could be like a validation point, this basically tells us how well it is to generalize it. Next, for our mean squared error, we're going to compare this to the baseline. So let's look at our baseline, which will be our linear regression model. Let's take a look at that. So our mean squared error score of our linear regression model is 0.004, which we can clearly tell that it's a lot smaller than our mean squared error we got for our random forest regressor, which suggests that our random forest regression model isn't as good as the linear regression model in terms of predicting. So next, let's plot it. Let's plot our results, and we can see here, if we take a look at here, our predicted values plateau and during the range of 225 and beyond months. This compares to the actual values, which continue to trend upward. So what we can definitely tell is that our model is not getting the trend. Although it looks like it might be getting the trend at first from, if you take a look at this section, that section, if you notice from this part, basically we concatenated our predictions with the original, so it should be expected for them to be the same. What we really want to focus on is this section and that section. So maybe we can improve our model's accuracy if we increase the amount of decision trees. So let's do that. So instead of using 200 decision trees, let's try aim for 20,000, 100 times more. So let's take a look at that. Okay, we can see that our model has finished training with our 20,000 estimators. So there's that. Now let's see how it works. So our out of bag score is a little bit higher, but more importantly, our mean squared error is 0.01 less than our previous one, which certainly serves as quite some improvement. Although, unfortunately, it is still not as capable as our linear regression model we trained here, which has a mean squared error of 0.00456. So let's look at the graph for this one. Still, quite similar to the previous one, it still plateaus. So let's see how the model works when it comes to predicting its original data. Notice here that the mean squared error this time is actually very, very low. And the out-of-bag score is still quite high, which means it's still quite strong when it comes to generalizing. But what this means, if our model has a very low mean squared error for data it has already seen, but when it comes to data it hasn't seen very well, it does not predict as well, so it has a higher mean squared error value, that basically tells us that our model is overfitting. So let's take a look at the predicted values this time. Still similar to plateauing. So with all that said, let's take a look at the model through cross-validation. So as we see here, our total MSE, basically, which consists of all 5 of the KNN, because this one uses K-fold cross-validation, we can see the 5 different versions of total MSE, and then we add them all together and we divide to get the average, which would be around 0.019. Just to conclude, we have seen that our model, the random forest regression one, has fared quite worse in comparison to the linear regression model when trained on the same amount of data. Although, when we increase the amount of decision trees, our accuracy certainly improves. Now, we also have seen that our random forest regression model is overfitting the data, which could prove quite troublesome since this is predictions. However, if we want to further improve our model, what we could do is we could certainly use, in a sense, better data. This project currently is limited to around a few amount of features. And the thing is, when it comes to inflation, there's a multitude of features, probably hundreds of features that must be considered when forecasting inflation. Hence, if we wish to truly be able to make a high quality evaluation of inflation for the future, it would be of best interest to pick a large data set and then train a model on that and to see what results come out. Thus, thank you for taking your time to listen.